Hello, so this will be the last video of this chapter. In this video, it's a continuation from the Bayes rule. So here, I'll consider another example that is based on my personal experience. So first, think about pregnancy. By the way, my son is 7 years old now. He's healthy, and when my wife was pregnant, so of course any parent would be concerned about baby's health, right? So and there are some screening tests so for birth defects like genetic abnormalities. So for example, it tests for Down syndrome, spine and brain problems, and there are many possibilities, even though they are very unlikely and really tiny probability for these kind of abnormalities. But parents worry about that. And based on these screening tests, positive results imply high risk, but negative results imply low risk. So I don't know how medically it works, but just to define some terms. By the way, also medically, I learned recently, preparing for these slides, I learned that medically there are two different terms. Diagnosis is different from screening tests. Diagnosis is confirmation. Really, it's certainly there is something. Medical condition exists, diagnosed, but screening test and positive result from a test does not confirm. It is just statistically the risk is high. It only means the risk is high, so it's not 100%. So what we are studying here, because we are learning statistics, we think of screening test. We never know with 100% probability. It's just high risk or low risk. Okay? So then in this example, what you can tell is during the pregnancy, you only know whether the test result is positive or negative. If you are positive, you just worry about the risk. Negative, then you will be more relaxed, but still it does not rule out the possibility. On the other hand, when the baby actually is born, you can certainly tell if the medical condition exists or not. So you have to wait until birth, or you have to do more tests, which could be medically dangerous. Anyhow, this is the situation. So 7 years ago, when my wife was pregnant, we were told that my baby was at higher risk, a positive result for abnormalities. So then think about this. So we learned positive result. Then given that situation, what is the probability that your baby does not have any birth defects? We know that positive result, and we hope for non-defect, no birth defects at birth. What is that probability? So the answer is C. What we already know is positive result, and what we hope is non-defect, right? The complement. So this is the probability we are interested in. We hope to know this probability, right? Okay, this is the answer. However, the problem is that probability is not what the doctor tells you. So at the time, doctor told me, oh, this screening test is very accurate. So detection rate is, say, 99.9%. That's exactly what the doctor told me. So detection rate is more scientific research terms. So when in the lab or scientists calculate the accuracy of the test, so they use detection rate. It is calculated defined this way. The probability of positive result when birth defects exist, right? Then how can you translate detection rate to our notation? So in the lab, in the medical lab, what they do is, I don't know, I have no idea about medical, but just imagine. So what you do is you have many sample uh, babies, or what do we say? Anyhow, samples, and that you already know that they have birth defects, like say sample genes, sample DNAs, and uh, you are doing some test on those samples and see how much of the samples turn to positive results, which is the correct result, because your sample consists of DNAs with birth defects. So you are testing them. That is detection rate. In that experiment, lab experiment, what they know is the sample already have the defects, birth defects, and based on conditioning on those samples, you'd like to get positive results, positive test result. So detection rate is calculated this way. Given birth defects, how many of them give you positive results? If this is high, then your test result, the screening test, is very accurate, right? You can detect that. So that is B. The answer is B. And what I'm telling you here is the relationship between these two is not that straightforward. We learned Bayes' rule to flip them, and this process is not easy. Okay, so then we have four types again. Actual, like D and D complement, whether the baby actually has birth defects or not, right? And on the other side, whether the test result is positive or negative. So there are four types. And when the baby has birth defects, positive result is correct. True positive. We say that it is true positive. But positive result is not 100% correct. So there may be false positive, which means the test result is positive even though actually the baby did not have any birth defect. So it's the test result is wrong, but we know that it's possible. So we cannot be 100% sure. So there is false positive result. And on the other side, even if you see negative result, it doesn't mean there is no birth defect. There is possibility that the baby actually has birth defects, but the test result was false. False negative. But if it's negative and the baby does not have any defects, then the negative is true. True negative. So in that way, you'd like there are four types of the results, and like a better test, a better medical test will have high probabilities on here and here, and close to zero here and there. False positive and false negative is close to zero, and true positive and true negative will be close to 100%. Like there are some should be 100% if the test is good. So in medical studies, they define terms like that. So detection or sensitivity rate is defined as the conditional probability of true positive given the condition exists. On the other hand, about true negative probability, it's called specificity and selectivity rate. That means a probability of true negative when the sample actually didn't have any defects, right? So this is scientific terms in medical studies, but that is not what we want as a parent, right? So then let's think about numerical example. I'll suppose that detection rate is 99%, very, very high. This is what the doctor told me at the time. And specificity rate is 90%. A little lower, but still very high. But additionally, I'll assume that birth defects exist for 1% of babies. By the way, these numbers are not true, like fake numbers, just simplified numbers, but actually the detection rate could be, specificity could be higher than these, and the actual probability of birth defects is much lower than 1%. So what I'm doing is just simplified numbers, but actual probability could be more extreme. But let's see what happens with these numbers. We are going to use tree diagram method. We are going to divide the imaginary sample into 4 types, and I will choose 10,000. I will think of 10,000 sample, say, baby DNAs, right? Baby DNAs. And based on them, I'm going to use the test to classify them, right? Then I ask you to do it first by yourself and find out what comes here, Z. Classify 10,000 into 4 types using this information and find out what is Z. Pause the video and do it by yourself. It may take a while. Okay, I assume you have done this, you have answered this by yourself. Let me do it. First, we start from 10,000 baby samples, sample DNAs, and I test them like first I'm going to use 1% unconditional probability. We know that 100 babies, 1% of 1,000, 100 babies have birth defects. Excuse me. But the other 9,900 babies don't have birth defects, right? So only 1% of 10,000, that's 100, have defects, and the other don't. Okay, first step, good. And then for the sample babies with birth defects, I do the screening test and see how many of them have positive results and negative results. So we know that the detection rate is 99%. That means out of 100 babies with birth defects, 99 of them will have positive results. 99% are detected, but the other one baby have negative result. So the birth defects is not detected for this baby. So, right, that's the false negative case. True positive, false negative. Okay, it's based on detection rate, conditioning on babies with birth defects. On the other side, 90% is the conditional probability of true negative. So out of 9,900 babies without any birth defects, 90% would have negative results. So 90% of 9,900 equals 8,910 babies. These babies will have true negative results. Okay. However, due to the 10% error probability, 10% of 9,900 will have positive, false positive results. That is 990 babies. Okay, so already it's done. 4 categories. So 4 categories filled into the 2x2 table like this. Of course, if you add those numbers again, you are going to get 10,000. Out of 10,000 sample, you have true positive, false negative, true negative. 4 types. Here, then, let's calculate the probability that I wanted. Calculate this probability. Okay, so once you have this 2x2 table, calculating this conditional probability is pretty easy. You delete negative results from the data, and then out of these many positive results, how many of them have the defects? This much. So the answer is 99 babies out of this much actually have birth defects. So the answer final probability is 9.1%. So this is very different from what the doctor told me. Doctor told me 99% correct. So that is not wrong. Scientifically, academically, that is how the measure. So it's true that papers, studies show that the screening test is 99% correct. But that doesn't mean my baby has birth defects with 99%. Actual probability is much lower because the pool size is different. Anyhow, birth defects are so rare. So rare. So even though you have positive probabilities, still this probability can be pretty low. So don't panic if you experience this. We didn't panic because also my wife is statistician, so still we are concerned a lot. So we did research after the result, but we are relieved by learning this. So I'm telling you, you may feel the same way. Then don't worry too much. I understand it can be worrisome, but it can be there is actually some kind of exaggeration. So don't worry too much. Instead of the tree diagram or like classifying one like 10,000 sample, you may directly apply the Bayes rule formula. It's up to you. So then we know first you have to write down the formula this way, and we know this, all the probabilities. Just fill the numbers, then you will get the same probability. So this is it. This is the end of the chapter 2. So thank you for watching. Chapter 2 is much more difficult than chapter 1. Of course, it will get more difficult as the semester goes. So I hope you to learn more, and you have to follow all these to follow the following later chapters because they are going to utilize what we learned here. Like independence is very important, especially for the later chapters. So follow me. Do not delay things, and do the homework and do the quiz, online quiz, and I will upload the guide video too. Okay, and if you have any questions, I'll be happy to see you. So I have office hours, and also you can send me emails to make appointments, or we can set up a Zoom meeting if you want. So have a nice week, and see you next week.